and head back over to where we left off. So this is the advanced session that we might do at the end. Otherwise, we'll now come to the last session that again includes some programming and some data modeling for, in this case, data modeling for particle data. So far we looked mostly at meshes, and with the example that I have prepared for modeling particle data, we will then also try to parallelize that and run it in parallel with, let's say, 4 ranks and see how things work there and what things you need to pay attention to. Just quickly, yeah. So we already saw particle data, we already visualized it. Again, this is the rough overview of how data is generally modeled in OpenPMD. So in here we see the E species from the simulation that we just inspected. E is for electrons. And as I said, the most basic component or the most basic record to describe particles is by giving their position and also their position offset for reasons of numerical stability, because you might want to be very precise, but be very precise in a high number range, and you can only really do that by adding an integer, a big integer, to a small float. So that's the reason for doing that. There might already be the question, okay, but if I don't need that, if I don't need the position offset, here it says the position offset is mandatory. How can I skip it? You see that in the next slide. And also, like meshes, data can be scalar or vector. In that case, the position is given by x, y, and z components. So you see here in bold that the x, y, and z component is defined for giving the position of, now what number is that? 109 million and something particles. Unlike the position, the weighting, for example, which we use again in PicOnGPU to model macroparticles and model the weighting between single macroparticles, is not a vector property, so that last x, y, and z thing is dropped. Let's look in the middle here first, because if we talk about charge and mass are also properties of particles, but they're physical constants, so it doesn't really make sense to write the same charge, the same mass 109 million times. Instead, for those kind of use cases where you have a value that you want to specify, and that you want to specify actually as a mesh or as a record or as a particle component, you can do that by an alternative representation which just stores the size of the dataset, here in this case as an attribute named shape with value 109 million, and then store the value once, and it's interpreted as being an array of 109 million times that value. We will see that in the upcoming exercise. Up at the top again, there are attributes for the electron species. Here again, not specified by the OpenPMD standard itself, but by the EDPIC extension. And momentum again is a regular non-constant vector quantity. So for example, if you want to store the position or if you don't need the position offset, you can set it as a constant component and set its value as 0, and then it will be ignored. And yeah, having that defined, or having this kind of constant component defined in the standard, means that readers will generally need to pay attention to data sets possibly being written as only attributes and only as a constant. There is a further little thing which will not be relevant for the exercise, but just as a little hint for what can be further done to describe particle properties. Because if you look, actually, it's on the slide. I actually remembered putting it on the slide, so I don't need to use the Blackboard. So down in the bottom right, you see a simulation box divided into 2 by 2 by 6 cells. And each of these boxes or subspaces is taken care of by one GPU. So the particles written by each GPU are within one defined small subspace of the entire space that is being simulated. So if you write the particles just as one long list, there is still some internal structure. And what we do in order to store that structure and retrieve it at read time, because a reader might want to look into the particles that were written by one specific GPU or that are found within one specific region, it might just not be possible to load everything because the particles might be 1 terabyte big. Then this is defined by the particle patches. The offset and extent gives the position within the physical domain, where the num particles offset and the num particles gives the position within the written array. So for example, for GPU 0, here in the slide as green, GPU 0 was in that simulation computing from 00 to 96, 512, 192 in simulation units. And we find those particles that are within that subregion in that slice of the vector. Just as a hint for if you want to store additional data for the directions where the particle mesh or where the basic particle mesh representation can be extended to. So we are now going to do two things at the same time. First of all, we are looking at the Python API now. So far we use the C++ API in order to further extend the Alpaca example, but I also wanted to show a bit how to use Python. And we are using that to add a constant component to an example that is prepared. So for that, we say goodbye today to the Jupyter Notebook. Record. Open again a Visual Studio Code session. And of course I need to default settings should suffice and launch it. We will start with 17 because sessions 15 and 16 are, as I said, the extra session that I have basically planned as a backup. I think we will have time for it. There is a question?
question in the chat right now, asking for the nexus of PMD conversion. Should we consider that already? So joining forces with nexus, whether you can comment on that.
Okay, there's the Sonal Patel's question on Nexus and OpenPMD. I will redirect you maybe to the workshop from a project that is currently planned on Nexus and OpenPMD. Wait a minute.
Sorry, it was not to you. It was the one who actually, I don't know his name, but the one who mentioned about some work on Nexus and OpenPMD. So sorry,
Okay,
it was not to you.
Okay, yeah. I'm also involved in that project. So René mentioned it, but I can. Okay, I have found it. There is that event on the topic happening in end of November, and that is the landing page for the project. So yeah, the status of that is that I'm currently trying to extend the OpenPMD API in order to be able to integrate Nexus classes into OpenPMD datasets. Yeah, and currently looking into how we can interact with Nexus data based on that. But it's, let's say, currently rather explorative still. In that case, let's go over to this right here. And okay, for now not, but yeah, we will later run things in parallel, so we might actually need to switch to the bare terminal. Let's see. This is a script taken from the examples that OpenPMD has. So I think I also, yeah, if you want to look at the basic example that's here, we will work based on that. And what we will do for now, so there is electron data defined, we will work with that later for parallelizing it. But the to-do comment is now here, because let's assume we want to store the temperature, and for some reason the temperature is a constant in our setup. Might be. We want to represent that fact somehow. I already pre-filled some information on the temperature mesh. Its unit dimension, its name, its axis labels, grid spacing is just a default. This one we can actually ignore with the last release, so this also works now. And in order to store some temperature, so currently this again only defines the metadata with reset dataset. It defines the data type and that we are in a 3x3 mesh. In order to store now a constant temperature, say temperature dot make constant, this is what will tell OpenPMD to create one of these constant meshes, and then just write any value into here, like this. Now, let's hope this works. So this is the line that we added. So the name write parallel is currently still a lie. It will become parallel in the next session. Okay. Source that thing. And we see this has created 8 files because we are writing 8 files in that example. And we don't even see the temperature by default because BPLS doesn't show attributes by default, but the temperature is a constant mesh which is defined only by attributes, so we don't see them. Let's switch on the attributes. And we see here the temperature mesh, including the value that we specified and its shape. I need to quickly try something because I noticed that from the Visual Studio Code session we might not be able to run things in parallel. I will try that next. Wait a minute. Let's try that. Because I'm already in a job, that's so I will need to hop into an interactive shell for the next session, but let that be a future sorrow. Anyone still needs time? Jurek, you need time? Okay. Or any questions? Otherwise I will continue. With some information on parallel file systems. So this is taken from the Lumi documentation. Lumi has a Lustre file system. This is not the only parallel file system, but a very widespread one. And just for giving you an idea of what a parallel file system is, and not just a black box that you write your data to, a parallel file system itself consists of several servers. Those can be metadata servers and object storage servers. Metadata servers are those that are upon reading or writing data need to be addressed first in order to find out where the actual data is distributed, because it can be distributed over several object storage servers, which themselves again manage several object storage targets. You can maybe compare it a bit to how your file systems on your local laptops also might fragment files if, for example, they don't find the space necessary for extending an existing file by the extra data that you want to write. So files need to be distributed somehow. In the case of a laptop, still on the same disk. In the case of a parallel file system, that can actually be several targets. And the key to getting I/O performance, because if we look, for example, at the 10 terabyte per second that I mentioned yesterday, which Frontier supports, you will not get those 10 terabyte per second when you write to just one single of those targets, but you need to make use of the parallel resources while keeping in mind, as I said, that it's a shared resource, and if you overload the system, you will kill other people's performance. One thing that is natively supported by many of these file systems, including Lustre, is file striping, where you can set on the command line a default file stripe, for example, for a directory that you're working inside. The configuration is by setting the stripe size and the stripe count. Stripe size refers to the size of each block within your data. So for example, set that as 1 megabyte, where data is then split and the next block is written to another storage target. And stripe count, usually a number between 2 and 4, is then the number of storage targets that are going to be used by the file system. And already when I say between 2 and 4, you might notice that you will not get the full performance of the system by doing that. And that is because file striping helps you with increasing your performance, but it's not really the end of what you can do. So the main use is for improving the speed of serial I/O, or for improving the speed of parallel I/O to a single file. But then already when you do that, you will very soon get issues in performance by having contention on the same file. So maybe even at low scale you can improve this way also the speed of writing to multiple files in parallel I/O. But the real deal is going over to subfiling by writing multiple files and using the parallel capacities of the file system that way. Now, the most simple way of writing multiple files is doing independent I/O. Every rank writes his information, but subfiling is more than that. Because as we already saw, when we map processes from n processes to one file, that at some point doesn't scale anymore. File striping can help a bit with that, but there's a limit. N-to-N scales up to a mediocre size, goes well if you have a small to mediocre size setup. But you will then especially get into the situation that you will overload the file system very soon. And here in this graphic, in this benchmark done with Warp X on Frontier, actually the flip around comes very late. So at some point, writing not one file per process, but one file per node becomes more performant because you have less effects of overloading the file system. But also in the below graphic you see, where at 512 nodes on Summit there wasn't even a huge benefit on 512 nodes from going from 1 writer per node to 6 writers per node. So what happened there, the file system was bombarded with 6 times the number of requests, but the performance there was no real performance improvement by doing that. So you are overloading the file system, might be without having a clear benefit. So generally, what subfiling is about is some compromise between these two extremes by writing from n processes to m files where m is a smaller number, which means that there are going to be aggregation schemes in order to aggregate data from several processes to one. And there is not one single aggregation scheme. There is, again, also not a canonical answer on how to do that. There are many different implementations. I think when the ADIOS team was developing the current BP version, BP5, that we are also using in this workshop, they implemented multiple aggregation schemes and just had to try out which one works best for most use cases, but you can still also select the others. In ADIOS, typically the default is that aggregation works within one node. In HDF5, it's a bit more complex because, as I said before, HDF5 has a structured output. So if you write in a very unstructured manner, this aggregation scheme will then have to figure that out and fix your bad writing pattern into something more systematic. And let's try that. So here we start with the parallel example, and might already, come on. I hope I will get parallel. Let's see. Sorry for that. Just quickly try where I am, if I can. That works, okay. So I have now this example again that we've just looked into, and this time we look at the electrons, because what we are now going to do is we are going to parallelize this code. For this I imported MPI and already prepared, no, actually not. You need to first add MPI or pass the MPI communicator that we are going to use into the series. Let's do that together because there's no real use in making you look up where to put that. Since the JSON configuration is optional, the communicator goes before that. And the general way that parallel output works in OpenPMD is that you create the structure on each parallel rank separately. And especially since in HDF5, writing attributes or defining attributes is a collective operation, you should if you want to if you want to have parallel output also work for HDF5, you should on each parallel rank define the attributes and define the entire structure like this. And the backends, in that case ADOS and HDF5, will take care of merging the information that they get from all the ranks into one file. And the attributes are not written in parallel, so while you define them on each rank, they will appear as one thing in the output. But what is written in parallel is the meshes. So we saw before when inspecting the Picon GPU data, if you remember, with BPLS-D for decomposition, we saw the decomposition where each rank wrote its little block. And the idea now is that we are here writing the electron positions. That is now still the code for serial I/O. And for serial I/O, it was relatively easy because we just said the electron, there are 10 electrons. So we specify the size there. Yeah, we reset the dataset, say, okay, the vector length is 10. And write all our local data to that dataset. Now, since each rank contributes 10 electrons, for example, if we run this with 4 compute ranks, this will be 40 in total. So the first thing that we will need to change is the total size of the dataset, by multiplying that with the comp size. And we are here now looking at an example where everything is homogeneous, but might also be that you have different numbers of particles contributed by each rank. Or that's actually the common case if you have a real world setup, because you cannot make sure that each simulation box has the same number of particles. Otherwise, your physics are probably boring. And in here, we now need to make sure to write to the correct position. So the particles from each rank are concatenated into the total array. So we need to write from that offset to the beginning of the next. So these are the changes that we need to make to this example in order to parallelize it. And as I said, we can no longer run this within the Visual Studio Visual Studio Code terminal, because that only has one parallel rank that we can access, but we want to run it in parallel. So let me first try if that works, because at home I tried this on a normal terminal and I'm not sure if it works as I expect here. So before all of you open this kind of terminal,
what do you mean by MPI rank? Sorry for interrupting.
we are going to run this with 4 MPI processes. Source. Seems to work. Okay, yeah. So you will need to either stay on the terminal that you've been using anyway, if you didn't use the integrated Visual Studio Code. Or you can launch a terminal here with the reservation that we've been using, specify 4 cores, and then launch that. And now let's make sure that the output is what we have expected it to be. So we have run it with 4 parallel ranks, and indeed we have 4 times 10 is 40 particles now written. Let's run minus d, small d, to see if the data was actually written. Looks like it. And we can run with capitalized D for the decomposition, and we see that we have 4 blocks per dataset. And in order to look at the aggregation that ADOS did, we can look into those folders .bp5 because they are folders. And generally, the actual data you will find in files called data.0.1.2 and so on. So since there's only one file, we see that the data was actually aggregated to one file. We can try telling ADOS to not do that and see how the behavior changes. By specifying up here an engine parameter. This is now specified as a JSON map. You could, as a Python map, you could also just write a plain text JSON in here and pass it on, but just for the fun of it. And let's say we set here the engine parameter to now let me actually look up what the name was. You see the engine parameters here. It's probably a good idea to read a bit through that in order to see what kind of options the aggregation and generally the I/O backends support. What we want here is the aggregator ratio, and we want to set it to equals 1, meaning that each process is an aggregator or there is no aggregation happening. So let's specify that as 1. Head over to the terminal. It doesn't matter if you put this in quotation marks or not. ADOS generally accepts string parameters, but we at some point added conversion from numbers. So run this again and look again into the folder, and there we see no aggregation has taken place. Instead we have data.0, data.1, data.2 and data.3, so aggregation was stopped this time around. Now, I already told you that aggregation can also be done by HDF5. I mean subfiling. This is also part of the recent OpenPMD release, so subfiling is very recently supported by OpenPMD. For this, we change the backend to HDF5. Let's see if I have the, yep. So maybe let's do it like this. As I said yesterday, you can have ADIOS and HT5 configuration side by side. And now I quickly need to look up the config structure that we have in OpenPMD for this. No. This is what we want to have, so the virtual file driver needs to be set to subfiling. So VFD as type subfiling. As you see, you can also specify the stripe size, stripe count here that I mentioned earlier. Just here it's for subfiling and not for striping itself. And maybe let's keep for the beginning the default VFD, which will write to only one file, so we see the difference later on. Remove the output folder. Run this in parallel. We see this created just normal regular HD5 files, which we can access the usual way. But if we actually use the subfiling VFD, we see that the subfiles are just written into there. So you can either use the subfiling VFD for reading those files back in, or alternatively there is a command called h5fuse. Now I need to look up, I think I wrote it somewhere in here. Did I? No. Did I write that in here? Yeah. Okay, for some reason I apparently wrote the documentation in the solution, okay? Because if we now run this h5ls, see what it actually does, it complains about the data not being there because it is in the subfiles. So for most regular HD5 tooling, in order to be able to read that file again back in without using the subfiling VFD, you would first need to okay, I cannot copy in that session.
It's Windows, you need to really Control-C.
I think I did. Okay. Let's do that. We didn't write lots of data, so the fuse went relatively quickly. And now it knows about the data again. Now I've switched between windows a lot, so if you want to see something again.
What is H5
Because if you look up at the output that we just created with the subfiling VFD, it has all of these subfiles distributed all over the place. So you can open the HDF5 file again without doing anything if you use the subfiling VFD also for reading. But if you use any kind of tooling that just has normal HDF5 routines, you will not be able to read that because the .h5 file only has the metadata and the actual data is somewhere out there. So you need to run h5 fuse in order to get data back into the main file from the subfiles. So you don't get this kind of error here. With ADOS, you don't need to do that because the ADOS file formats have been written for subfiling from the beginning and natively. So even if you write with one single parallel process, there will be one subfile, and ADOS is implicitly subfiled, so you don't need to fuse after writing. In HDF5 you do, because you need to get data back into the format that most readers expect.
So in terms of creating master files,
It creates one file that actually has all the data. So even if you use parallel output, there is one master file here, but the master file doesn't contain the actual data. So H5 Fuse puts the actual data back into the master file, if you want it like that. Now let's have some little fun and actually try what the JSON backend will do when running things in parallel. This is something that has been built into OpenTMD also with the latest release. Until very recently, the JSON backend didn't support parallel I/O at all. We now have some kind of limited support. I misconfigured. Did I not save? I'm in the wrong file. So now if you create a JSON output in parallel, this will again mostly useful for debugging, create n different subfiles of JSON, each containing the data that was written by that subfile. So if you run into any bugs, especially when writing data in parallel, you might wish to use that in order to see where things went wrong. And if you look into one of those subfiles, you will see that it has data only from that parallel rank, but not from the others, and the metadata that was defined by that rank. So there's no aggregation at all happening, but only that.
so there will be lots of nulls.
There will be lots of nulls. This is for the next release. I'm currently working on a reduced version of the JSON output that skips the actual dataset writing and will print only the dataset metadata. That's also part of the reduced output format that we need for the experiment setups that I mentioned yesterday. So that already works, but it will be part of the next release, not of the current. All right, that was what I wanted to tell you about for Parallel I/O. This means I have now half an hour left for the little session about improved memory improved workflows. And the afternoon session we can probably skip then and directly begin with the pick on GPU part and have an earlier weekend for everyone.